Hey, have you ever stopped to think about what connects the plastic in your phone to the very DNA inside your cells? It sounds crazy, but there's a single element at the heart of it all. Today, we're going to unlock the world of organic chemistry, the incredible story of how one element, carbon, literally builds our entire world. Okay, right off the bat, just look at this number. Over 16 million. That's how many different compounds we know about that are built from just one single element as their backbone. It's an absolutely mind-boggling number when you really think about it.
So the big question is, why? What is it about this one element that makes it the absolute superstar of the chemical world? What's its secret? Well, let's find out.
And yeah, you guessed it. That superstar is carbon. To really get what makes it so special, we've got to dive into the whole field of science that's dedicated to it. So what exactly is organic chemistry? Well, it's the study of carbon, and it's the reason we have those 16 million plus compounds. It's the foundation for modern medicine, the plastics filling our homes, the fuel in our cars, and yeah, the very DNA that makes you you. It really is the chemistry of life.
All right, to understand how carbon can build something as complex as DNA, we have to start simple. I mean, really simple. So let's meet the most fundamental family of organic compounds, the hydrocarbons. Hydrocarbons, the name kind of gives it away, right? They're molecules made of only hydrogen and carbon. That is it, nothing else. These are the absolute ground floor building blocks from which all that amazing complexity we talked about begins.
Okay, so we're in the hydrocarbon family. Now, let's zoom in even further to the most basic group of all, the alkanes. Seriously, think of these as the first, simplest pieces in our molecular Lego set.
Alkanes form something called a homologous series. Now that sounds fancy, I know, but the idea is incredibly simple. Imagine you have a chain of Legos, and all you're doing is adding the exact same block, a carbon with two hydrogens, over and over and over again. Each new molecule you build is just one identical block longer than the one before it.
And you can see that Lego-like pattern right here, perfectly laid out. We start with methane, right? That's your basic natural gas. Add one more of those Lego blocks, and boom, you get ethane. Then propane. Yep, the stuff in your backyard grill. See the pattern? With every step down this list, we're just adding one carbon and two hydrogens. It all follows that one beautiful, simple formula, CnH2n plus 2.
Okay, so now that we have this whole family of molecules, we need a way to talk about them, a common language. So let's check out the really clever system chemists came up with for drawing and naming these things.
And chemists, you gotta love them, they have their little tricks. To remember the prefixes for the first four, just remember this silly phrase, monkeys eat peeled bananas. That's for methane, ethane, propane, butane. Easy, right? After that, it's a piece of cake. It just uses the Greek prefixes you probably already know, like pentagon for pentane, hexagon for hexane, and so on.
All right, let's try to draw one. We'll use butane. First up is the expanded formula. Now think of this as the super detailed high-resolution blueprint. It shows every single atom and every single bond connecting them. It's crystal clear. But you can probably imagine how this would get super messy really fast with bigger molecules.
So to clean things up, chemists came up with the condensed formula. This is a much neater way to do it. We just group the hydrogens with the carbon they're attached to, so you get CH3, CH2, CH2, CH3. See? It's the same exact information, just in a much tidier, more compact package.
And then we have the final form, the skeletal formula. This is the ultimate pro-level shorthand. We don't even bother drawing the carbons or the hydrogens on the main chain. Every point, every corner, and every end of a line, that's a carbon atom. And we just assume the hydrogens are there to fill in the gaps. It's fast, it's clean, and honestly, this is how most organic chemists actually draw things. So far, everything we've looked at has been a nice, straight line. But here is where carbon's real magic starts to shine. Because those chains, they don't have to be straight. They can branch.
And that branching brings us to this super important idea, isomers. Just look at these two. On the left, we have a straight chain, N-pentane. The N just means normal. On the right, we have isopentane. It's branched. Now here's the kicker. They both have the exact same formula, C5H12, but they are totally different compounds with different properties. This matters a lot in the real world. Think about gasoline. The more branched the molecules are, the higher the octane rating and the better your car runs. So just by changing the shape, you create a whole new substance. How cool is that?
This ability to form chains and branches is already amazing, right? But believe it or not, that's just the beginning. Now let's see how carbon goes from being a simple skeleton to the foundation for, well, basically endless possibilities.
Because the real variety, the reason we have those 16 million plus compounds, comes from attaching other atoms. Things like oxygen, nitrogen, sulfur. These little attachments are called functional groups, and you can think of them as giving each molecule its own unique personality and chemical powers.
Let's just take oxygen, for example. You snap on a simple hydroxyl group, an OH, and you've just turned your simple alkane into an alcohol. You arrange that oxygen a little differently into a carboxyl group, and suddenly you've got an acid, like the one that gives vinegar its sharp kick. These different arrangements are behind everything from industrial solvents to the sweet flavors in fruit.
And it just keeps going and going. You can add sulfur, and you get these thiol groups. They're responsible for that, unmistakable smell of garlic. Or you can add nitrogen in what's called an amine group, and now you're talking about the building blocks of life itself, the amino acids that make up every single protein in your body. The carbon chain is the backbone, but these functional groups are what let it build pretty much anything you can imagine.
So just think about the journey we've been on. We started with one element. We built simple chains, then we made them branch, and then we started decorating them with this huge library of functional groups. We've literally built a universe of molecules from the ground up. And it all leads to this one last, kind of mind-blowing question. If simple lines and branches can do all of this, what in the world happens when those carbon chains decide to loop back and connect with themselves to form rings? Well, that is a whole new dimension in the incredible world of carbon.